Good.
Hello everyone, my name is Chris and I'm from University of Oxford from the DFU group Infom. So our team has been working on the flood risk management measures on river networks. So first I'm going to begin with a little overview of what we've been doing and what I'm going to present now. So first I'll give you a small background, a recap on what we did during the week. Then I'm going to present several models which we use to tackle the problem, some numerical results and examples, possible failures of our model and what we're going to present about, and an optimization algorithm which will attempt to give a solution to the problem. So, first things first, recently people have been interested in nature-based flood risk management measures, of which small-scale runoff attenuation features are an example. So here we'll be focusing on a very simple device, which we're going to be calling a leaky dam, which you can think of as a bunch of logs stacked on top of each other across a river channel, with a certain gap between the river bed and the dam itself. So the idea is that this device will help delay any flooding by holding back and storing the water behind it, which will eventually reduce the flood risk, which is our goal. So questions which we'll try to answer in this presentation is, first, how do we model a river network flow without any dams? This will be our basis for our model. Then what happens if we include one or more dams? What's the effect on the flow of this thing? How effective are they? Whether there is, if at all there is any effect, and if there are any failure mechanisms. So back to the model. So we're going to employ a simple network model with vertices and edges. The vertices being the channels, and the edges being we can think of it as flow between the channels, or the potential space where we can place a dam or not. So each vertex or channel will be associated with a certain set of parameters, physical parameters like dimensions of the seabed, roughness, slope, and etc. And for the flow, we will have an inflow condition, which usually we're going to model as a Gaussian. So this will be our flood, Gaussian in time, on the global network. And we're going to have a conservation law for each node, which I'm going to present on the next slide. This is just a sample diagram of a network, river network. So, as I mentioned, we're going to use first, we're going to start with a simple 1D network, meaning you just have a chain of nodes without any branching. And we're going to use a very simple conservation law of this form. So on the left-hand side, L is the length of the channel, A is the average cross-section. So you can think of this term as the rate of change of the volume of water. Whereas on the right-hand side, you have the net flux in the channel and a source term, little qi, which will come from rainfall or other runoff from the lateral length on the riverbed. And we'll have this law for each node, for each vertex, I from 1 to n. So in order to close the model, we'll need an expression, we'll need a way to express the cross-sectional area and the flux. So first, we're going to focus on a rectangular cross-section. I'll just explain what I mean by this. So this is our dam here. This is the riverbed. And the water is here. So we'll split this region into two. So first, before the water has hit the dam, so you can think of the water as just a uniform layer. So the cross-section will be simply the width times the height. Once the water hits the dam, you have to add on this triangular volume, so it's like a pyramid if you think in 3D. This is a cross-section. And so in order to get the average cross-section, we're going to calculate the volume of this pyramid. We're going to divide by the length, and this will give us the average cross-section, rectangular cross-section of this flow, which is represented by this term here. So, furthermore, we need an expression for the flux. So again, we're going to split the whole flow in different regions. First, we're going to have an expression for the flow before the water has reached the dam. So this is simply gravity-driven flow counteracted by drag on the riverbed, and is given by the so-called Manning's law. And here n is Manning's roughness coefficient. Then once the water hits the dam, you can imagine it starts accumulating behind the dam. So we're going to have two terms here. First, the classical sluice flow, which you can think of, we have a reservoir of water and a hole in it. And how do you describe the flow? This is given by this term. It's a simple application of Bernoulli's theorem. And we're going to furthermore assume that the dam is permeable, because after all, it's comprising of several logs stacked on top of each other. So you can think of it as water passing through them with a certain permeability coefficient, which we'll call K. Finally, once the water reaches the end of the dam, it will overflow, and then you'll have an additional term, which comes from the water passing above the dam. I'm going to show you a picture in a second. So in the previous model I described, you can imagine you don't have these triangles here, the regions 4. You just have 1, 2, and 3. This is the water below the dam, while it's accumulating behind the dam, and when it's overflowing. Now, in order to improve storage, we decided to employ an even more realistic model, which takes into account of the widening of the riverbed. So we add on these two regions 4 here. And then we have a trapezoidal average cross-section, which just adds on this term to the expression for the overflow flux, for the flux from the overflow region. And this improves storage, as I said. Now, so far we've considered 1D case, but you can think of the river network as a much more complex structure. So you can have branching. So you can have the main river here and some tributaries coming from the sides. So the conservation law for each node will be pretty much the same, except that you're going to have a summation over all adjacent nodes, which branch into this node. So that's why you have a summation over all adjacent nodes. Aij are entries in the adjacency matrix for the network. So we've decided to look at the effect of the dams on the mainstream. So on this main river here, as opposed to the effect of the dam on these branches. So on the top, you see graphs of the maximum height of water stored behind the dam versus the height of the bottom of the dam on the main river. Whereas on the bottom you see the same, but versus the height of the bottom of the dam on the branches. And we're going to explore the effects of these two. When we vary the height of the dam, what happens to the maximum height of stored water. So first, we assume on the left, you see when we assume a little rainfall. So not the peak of this Gaussian that I said is going to be small. So we see that as the height is very small, so there is a very small gap between the riverbed and the dam, you can see that the maximum height increases, which is what you would expect. Imagine you have a bucket of water and a small hole at the bottom. If you pour in water, obviously the height will grow. Whereas as you increase the height of the dam, because the rainfall is not so much, at some point it will just flow, and there will be no flow under the dam, and there will be you won't be able to see the effect of the dam because the rainfall is small enough so that all the flow passes under the dam. That's why eventually it becomes constant. You don't see any effect of the dam. Now, when you increase the rainfall, so you can imagine you have a real flood, then what happens as you decrease the height of the dam, the height of the stored water, of the water that comes out in the end, will be much smaller as opposed to when you have a bigger height, which shows the effect of the storage of the dam. So basically, when you have smaller gap, you store more water, i.e. less water is coming out at the end of the network. Similarly, when you look at the effect on the branches, the dams on the branches, we don't see any effect. So this says that we should focus mainly on the main river branch, on the main river in the 2D network. That's where our effort should go in. So now I hand over to Ian, who will continue with some numerical examples and optimization algorithm for the problem. Yeah, now. Yeah.
Is that working? Okay, so I'm going to just show you a few more examples that we've looked at and some of the sort of things that we can analyze with this model. So what you see on here are this is now a one-dimensional network. So forget about all of the branches and just imagine that main trunk of the river. And what you're looking at is what would happen as a function of time at each of the different segments of the river, which are represented by different colours, if you didn't have any dams and if you did have some dams. Okay, so here on the top you see the discharge, which is like what's flowing through where there would be a dam, and here is the height of the water behind what would be the dam, and then here it actually is the dam. And of course you can do this with like hundreds of segments of the river, but it becomes a bit hard to see what's going on. So here we've just chosen an example where you've only got 5 of them, so that you can see it. And in this particular example, we've got water feeding into the river all the way down, so they're all collecting the water from upstream as well as what comes in from the sides. So the discharge flowing through the river increases as you go down, which is why so blue, red, yellow, purple, green is moving downstream. Okay, so here we've forced it with the Gaussian, which is what Chris was talking about before. So there's nothing, and then this is a storm, and then it dies off again. And in the case with no dams, there's essentially no lag. We haven't put any lag from the overland flow in this model, so the flow downstream basically responds to the rainfall almost instantly. The dashed line, there's a black dashed line there, which is the actual total rainfall input. And so you can see that when you put in the dams, you slightly delay the flow through all of the segments, which is because of the storage effect of the dams, and you also slightly decrease the peak, which is of course what you were trying to do. You want that green maximum to be below what it would be if you didn't have the dam in place. Okay, so what you see here is then the storage behind the dam. So these dashed lines here represent the heights above the bottom of the river of the bottom of the logs and the top of the logs. So you can see, so here the dam comes into effect, and then fairly quickly it fills up with water, and then it starts overflowing, which is what's happened up here.
There is no delay between the dams. Is it because you shifted everything?
You mean why do these all look the same?
No, why are they all at the same time? Why does the peak arrive all at the same time?
So here we're assuming that there's a rainfall, which is loading the land, and then the water from that is flowing into the stream. The rain is uniform, so it's not somewhere upstream, it's uniform.
Okay.
And so in reality there ought to be some delay between when it falls on the land and then when it gets into the river,
Yes.
which we've neglected. So you can imagine that the rain actually happened at time, say, -1. There is a time delay of 1 for the water to get into the river, but because it's coming from all sides, it arrives at all segments of the river at the same time. But that's why the peak's at the same time.
Yes, okay.
There's of course, I mean, there's sort of lots of ways that you can play with this, and I mean, in the end, we'd like to do a real example. But it's quite helpful to look at simple situations like this just to get a feel for what's going on. There's various blips in here which are associated with changes in the flow when you suddenly hit the dam. There's a sudden change in the flow of the water which is regulated by the dam, and that gives you these funny blips. Okay, here's just another example. This is now this sort of herringbone pattern, which was shown earlier. It's actually on the board over on the left there as well. And this is now, suppose we have the same situation where there's a big storm, and suppose that we've got 4 dams that we can put in place, because that's what we've got the money to do. The question is, should you put them on the main segments, the trunk of the river, or should you put them on the sides of the river? Okay, this is the sort of thing that you might be able to analyze. So this is what happens if you put your 4 dams on the main trunk. You get some effect, and the maximum Q is 15.1. This is the Q, this is the flux that's coming out of the bottom of the network, which is the one that you need to worry about because we're assuming that's where the village is. The maximum, if there had been no dams at all, would have been 16. So there's been some slight delay. And then this is what happens if you put the dams on the branches, which seems to be marginally better, although the difference is really quite small. It then turns out that it was even slightly better. This is if I put the four dams on sort of one side of the valley. If you put them all at the top of the valley, on both sides, that turned out to be slightly better still. And it's not totally clear why that is, but that's the sort of thing that we could look at. Okay, so then we've looked at failures. Okay, this is an unfortunate name for a slide. We had lots of failures. MATLAB gave us lots of failures. But this doesn't mean our failures. This means the failure of the dam. So we were trying to analyze what would happen if a dam collapses, because that's obviously one of the things that you need to worry about. And particularly, would it make it worse to have the dam in place than it would have been if the dam hadn't been there at all? So we were given this thing which is called a fragility curve. So this says the probability as a function of water level that the dam will collapse. At least that's how I interpret it. This is like a cumulative probability distribution. And the different colors represent different conditions of the dam. So a really good dam would be the lower curve here, or the one on the right, which needs a high water level before it's likely to collapse. Whereas the light blue one here is a really rotten dam, where you hardly need to hit it at all and it'll just disintegrate. And so you can think that over time the logs will age and you'll get more to being like on the light blue curve. So we take this to mean that for each dam there's some critical water level where if you hit it with too much water it will just collapse. So we could implement that in the model and just say that the dams will disappear if the water level gets to a certain height. And now I have a video, I hope, to show this. So the question was, if the top dam fails, does that lead to a cascading effect where the rush of water from that dam will break the next dam and then so on, and like knocking over dominoes? So here is a movie. I think this goes a bit fast, so I'll play it again. So what we're looking at here, and it's just going to keep playing, so that's good. So here you're looking at 20 segments of a river. This is a linear river. There's 20 segments here. What you're looking at is the height of the water behind each of the dams. It's represented as a continuous line, although there's really only 20 numbers there. And the black dots here, so they're everywhere, they represent the bottom log of a dam. So down here the dams are not in operation, and then as you go further downstream the dams are in operation when it's above the black line, and the red line is the critical height for which if you go above that then the dam breaks. So that first happens down here. So this is a time evolving simulation where there's some background rainfall which causes the flow to increase as you go downstream, and then we hit it with every now and again a pulse like that, which is a storm, which comes from upstream somewhere. So, okay. So what you're most interested in here is the first one. So let's just wait for it to start. Look at the way that the dams collapse. Okay, it's a bit too quick to see anything actually. Let me see if I can stop it. You think I can slow it? Well, let's just stop it. Oh, that's the wrong place. Okay, so what happened here is that some of the dams low down the river have collapsed. That's just because there's so much water downstream, and we've built dams of the same strength everywhere, which is not what you would do in reality. But so the ones downstream are being wiped out simply because there's lots of water at the end of the river. The one upstream has been wiped out because of this big pulse that hit it. But then the next ones are okay. And then what happens after this is a bit bizarre, and we were not expecting it. Is that one of these dams here is the next one to fail. And so this is a kind of version of this cascading failure, but it turns out that it doesn't just knock them all down in sequence. It knocks some of them down. Some of them were closer to the critical level before the storm came along, and therefore they need less of a hit before they break. So this one here was already closer to the red line. So the perturbation that comes from the storm is sufficient to cause it to reach the failure level, and then it collapses. Whereas the ones that were back up here didn't have so much water in to start with, so they didn't have enough of a kick to make them break. So if I just let it keep going, then you should see that somewhere in the middle is the next one to fail. Oop, there it's gone. Okay, so that was slightly unexpected. What we have not done is to analyze very carefully what was the effect of all of this on the discharge downstream. The reason we haven't done that was because we tried it and it gave some peculiar results that we haven't managed to explain. But that's something that we can try to do. Okay, so we've investigated this possibility of cascading failure. So another failure mechanism was that the flow underneath these dams is quite fast because you've constricted it, and so it's likely going to cause some erosion underneath. So this is commonly occurs underneath sluice gates. So here's just a sort of schematic of what might happen. So here's the stuff behind the dam. The water's going underneath, and that's going to scour out this, and then that will make the whole thing less effective because there's now a bigger hole for the water to go through. So we haven't really analysed this very carefully, but we thought about how to do it. So the suggestion was that we could add an extra depth of eroded material underneath the dam, which we call D, and that we write down some law that's an erosion law that looks something like this. And basically there's a term here which is proportional to the flow through here. This is a sort of fairly typical description of river erosion. And so this tau is the stress which is exerted by the water flow on this. And so over time, you will keep enlarging this gap. And then you feed this back into the rest of the model by increasing the height of, effectively we're increasing the height of the bottom of the dam above the bottom of the river. But we're actually lowering the bottom of the river. So this is our suggestion as to how we could fairly simply examine the effect of erosion on the performance of the dams. Okay, so we also looked a little bit at optimization. And so the model is sufficiently simple that you can think about questions like where is the best place to build the dams, or what is the best height of the dams to pick to have the desired effect. So this turns out to be actually quite complicated, so we haven't got the full result of doing this, but let's just explain the way that we thought about doing it. What we're interested in doing is avoiding a flood, so we need to do that. We want the best dam design, and we want to do it at a minimum cost. So this is a way that you can frame the problem. Yeah. Okay, one of the ways that we can set this up is to say that there's some cost function associated with building the dams, which is what we were going to try and minimize. So, and in this case, we decided, well, maybe that's just the amount of material, or a measure of it is just the amount of material you need for the dam. So that's this h minus b is the total height of the logs that you need, and there's some cost associated with each of those. So you sum all of that, and you want to try and keep that minimum, subject to the constraint that you need to keep the height of the water at the last node below some critical level, which is when a flood would happen. And that's a way that we can frame this. We want to do this, in reality, we want to do it for all sorts of possible forcing that might happen. So all sorts of rainfall forcings, we'd like to try and make sure that the height is always below this level. Of course, that's not going to be possible it's not always going to be possible to do that. So we have to sort of constrain the sorts of forcing that we give it to something that we think is most likely. So one of the things we thought about doing was just giving it one of these storms, like the examples that we showed you, and saying, okay, for a storm such as that, can we make sure that this happens? Okay, even that turns out to be quite a complicated problem to do. So what we've ended up doing for the moment is just looking at a steady state version of the model, where we say that there is a prescribed flow, and given the prescribed flow, can we do this and find out what the best thing to minimize the amount of material that we need is. So that's what we've done here. So this is using a sort of minimization algorithm applied to the steady state equations with those cost functions. And this says it's an optimal solution. So what you're looking at here is, again, 5 dams going downstream in a one-dimensional river. The logs, these are the logs. This is the dam, and the blue is the water level behind the dam. Most of them are overflowing. And this is the one down here, which has been needed to keep below a critical level. This says optimal solution. In fact, there are loads of optimal solutions in this case. It turns out that it almost doesn't really matter what you do. What the minimization algorithm tells you should do is have the dams be as small as possible, use as few logs as possible. And so in order to get this to look at all reasonable, we've actually had to say that there's a minimum number of logs that we want to use for each dam, which is why all of these things have got height 1. These are all of length 1. This is some scaled units. And so we told it that we didn't want them to make it any smaller than that. So the example that we picked and looking at a steady state turns out not to be not to have a very interesting solution, because you can do it in lots of different ways, and apparently the optimal thing to do is to have the dams be as small as possible. So essentially you just go and throw one log everywhere along the river. So the reason for this is that the point of having the dams was to store water in the case of a flood and to have some delaying effect. And so by looking at a steady state, we've kind of eliminated any advantage of actually having the dams in the first place. So the minimization algorithm is correctly telling us that we should minimize our cost by not doing this at all. Okay, so obviously this needs a bit more work to get some advantage of the dams to come into it. Okay, there was an alternative approach we discussed, and I'll stop in a second, which is actually very similar, which is to think about the whole thing in terms of transit times. So you think about each node of these network as having parcels of water which take a certain amount of time to get to the next node of the network, and we introduce some rules which are a bit like our formulas for the fluxes for how long that takes and how it's affected by the presence of the dam. And then you set up the optimization problem in a slightly different way, which is to say, suppose you have a certain number of dams, can you minimize the amount of time that you spend with the water level above a critical level? So this is like a measure of damage caused by the flood, and that's what you want to minimize. This is a slightly backwards way of solving the same optimization problem. So this was another way that we thought about doing it. And then I will conclude by saying that we have derived a pretty simple model with which you can do lots of exploration. So we just derived some hydraulic expressions for the fluxes and the volumes of water. We've shown various examples of solutions of the effect of the dam. It doesn't delay it by very much, which was already known. You need lots of dams to have much effect. And there's lots of scope for investigating further and doing optimization problems. Thank you.
Any questions? But first I will let the stakeholder react.
Well, thanks very much, and thanks for all your hard work and sort of shedding a lot of insight into some of these problems. I think it's really useful to explore and look at the problems, take them apart and really understand what's going on. And there's some surprising sort of outcomes in terms of the failure of the dams and no particular sort of domino effect. That's interesting, and we'll take this away and sort of help us think about the problem more, because I was at a conference the day before yesterday, and there's lots of people putting these structures in where they fail to get granting aid and just putting them wherever. So anything that can help us with strategies is useful. I would be interested to sort of tease out more about the patterns, sort of using these models to understand the trade-offs between the desynchronization that you might get by targeting every other and what happens then when you add failure into the picture, because not many people are modeling failure. So thank you very much.
Further questions? You pass it off to
Hi there, this came from the video you gave of the failing dams, and I think you said the black dots were the bottom log in the dam. Did you assume that once the bottom log had broken, the dam was completely ineffective? Because if you had, in your other picture, about 8 logs constituting a dam, if you lose one, then it may be that it has a attenuated effect, but it still has an effect. Could you maybe clear that up a bit, please?
Yeah, so what was plotted on the pictures was only the bottom log, and the dams actually extended upwards quite some distance from that, and we just didn't plot that because it would have taken up the whole diagram. We assume that if a dam fails, the whole thing collapses. So you only saw the bottom log disappearing, but simply because that was the only thing that we were plotting. But our assumption is that when it collapses, the whole thing just gets blown away. An alternative model would be to assume that the thing gets eaten away gradually. So assume that the bottom log gets eroded, and then the next one might somewhat later. And you could do that by introducing a term that's a little bit like the model I presented for erosion, I think, where it happens gradually. So our assumption was that there's a critical level above which the whole dam just collapses. I don't know what's more realistic.
Thank you.
Further questions?
I was just sort of curious if you've made any distinction between other options you could consider. So you've got your sort of your natural log attenuation scheme. You could equivalent just have sort of upstream storage, or you could just have sort of a concrete structure which is semi-permeable, which would not necessarily fail as often as in the log case. So did you consider sort of alternatives and actually whether we should be pursuing these sort of schemes, or whether something a bit more like hard engineering would be more appropriate because you'd avoid the failures then?
So we didn't sort of explicitly consider other options. I don't think there's an awful lot of difference. I mean, these things are sort of elements which could represent logs, but they could equally well represent a fixed dam. Of course, if you're going to have a concrete dam, that's going to cost more and be stronger, and so there's a competition between whether you don't want it to fail sufficiently much that you're going to spend more money to build it, and I think building larger storage reservoirs similarly might cost more money. So I think you could explore such questions within the framework of this kind of thing, and you might just change the parameters slightly. So the failure criteria for a concrete dam would be much higher than the failure criteria for a log dam, for instance, and then you could actually look at what's the payoff of that. But we haven't explicitly looked at those sorts of questions.
It was to do with the question that was posed, which was in particular the catchment that we've been looking at and basing the work on. The land was quite agriculturally productive, and they didn't want to flood it, and also it was a low cost solution, so we couldn't put in concrete.
All right, let's thank the group. Thank you.